Welcome to the Explainer. Have you ever caught your reflection in a spoon and thought, wait, why on earth am I upside down right now? Well, today we're going to answer exactly that kind of question. We're embarking on a super fascinating journey into the absolute mechanics of light. We'll be following the path of a single ray, from its vibrant source all the way to the elegant mathematical formulas that actually define its behavior.
Here is our roadmap for today. We're covering 1. Basics of light, 2. Laws of reflection, 3. Real versus virtual images, 4. Spherical mirrors, 5. Ray rules and uses, and finally, 6. The math of magnification. Let's get right into it.
All right, starting things off with Section 1, Basics of Light, Form, Energy, and Sight.
So, to really get a grip on optics, we first have to recognize that light is, at its core, energy that literally gives us the sensation of sight. Establishing our vocabulary early is absolutely crucial here. Think of a ray as just a single straight-line path of light. But a beam, that is a whole bundle of those rays traveling together from a source in a focused direction.
Now, depending on where they come from, these bundles of rays basically behave in one of three ways. You've got your parallel beam, where rays stay perfectly side by side. Think of a laser pointer. Then there's a convergent beam, where all the rays rush in to meet at a single intense point. Or they can be a divergent beam, physically spreading outward from one origin point. You know, just like your standard flashlight.
Moving right along to Section 2, Laws of Reflection, the bounce.
Okay, so what happens when this traveling light slams into a highly polished surface like a mirror? Well, it bounces. We call this reflection. And this bounce into the same medium is governed by two totally unbending rules. Step 1. The incident ray coming in, the reflected ray bouncing off, and the normal, which is just an imaginary perpendicular line right at the surface, all exist perfectly in the exact same plane. Step 2. The angle of incidence is absolutely always equal to the angle of reflection. So if light comes in at a 30-degree angle, it is bouncing off at exactly 30 degrees. No exceptions, ever. Which brings us nicely to Section 3. Real versus virtual images, convergence and divergence. When these reflected rays actually converge or diverge, they create an image. And that image falls into one of two dramatically different categories. A real image happens when light rays physically meet. Because they actually meet, you can project this onto a real screen. But, and here's the catch, it's always going to be inverted or upside down. A virtual image, on the flip side, happens when rays only appear to diverge. You can't catch this on a screen because it's essentially an optical illusion forming behind the mirror. But it will always be erect or right side up, exactly like what you see every morning in your bathroom mirror.
Next up, Section 4, Spherical Mirrors, the Anatomy of Curves.
To manipulate light into making these specific real and virtual images, we rely heavily on the precise anatomy of curved mirrors. To wrap your head around this, just imagine a curved mirror as one tiny slice of a complete hollow sphere. This mental model makes it so much easier to define the physical landmarks. The aperture is just the width of the reflecting surface itself. The pole is the dead center point of that reflecting surface. And the center of curvature? Well, that's the exact center of that imaginary hollow sphere we just talked about.
But the real magic? That happens at the focus. This is a specific spot on the principal axis, which is just an imaginary line passing straight through the pole and the center, where parallel rays either actually meet or appear to come from after they bounce. The distance from the pole to this focus is our focal length. And the math here gives us a beautiful constant. The radius of curvature is always double the focal length. Simple as that.
With our mirror anatomy locked in, let's look at Section 5, Ray Rules and Uses, Plotting the Light. Now we get to actually map out exactly how light behaves. When drawing a concave ray diagram, light is incredibly obedient. It follows three sequential steps every single time. First, a ray traveling parallel to the principal axis will reflect directly through the focus. Second, we see the exact reverse. A ray passing through the focus will bounce out perfectly parallel. And third, a ray passing through the center of curvature takes the path of least resistance. It hits the mirror and just retraces its exact original path backward. Boom, done. If you look closely at this data, a seriously cool pattern emerges. The image created by a concave mirror completely shapeshifts depending on where you put the object. As you move an object progressively closer to the mirror, the image shifts from being real and tiny to real and same-sized to real and massive. And then, magically, if you push the object super close, right between the pole and the focus, it suddenly flips. It becomes a virtual, right-side-up, and highly enlarged image behind the mirror.
Now, unlike that crazy shape-shifting concave mirror we just looked at, the convex mirror is incredibly predictable. A convex mirror curves outward, and no matter where you place the object, it only ever produces an erect, virtual, and diminished or small image behind the mirror. It does one thing, and it does it well.
So here's a real-world question for you. Why do completely different professions rely on completely different mirror curvatures in their day-to-day work? Like, why do dentists need concave mirrors, but our cars use convex mirrors for rear viewing?
Well, it really comes down to what we need the light to do. Dentists, or even just folks shaving in the morning, need a concave mirror to heavily magnify the image so they can see all those fine details up close. We also use concave mirrors in headlights to forcefully concentrate beams of light straight down the road. On the flip side, drivers absolutely need convex mirrors. Why? Because by shrinking the cars behind you into smaller, erect images, you actually get a vastly wider field of view of the traffic. It's all about purpose.
Finally, let's dive into Section 6, the math of magnification, calculating the bounce.
Okay, so everything we've talked about today is ultimately governed by the mirror formula. 1 over f equals 1 over v plus 1 over u. It might look abstract at a glance, but this single elegant little formula mathematically links the focal length f with the exact calculated positions of your original object u and the resulting image v. It ties the whole shebang together.
And then we have magnification, which simply tells us how much larger or smaller the image is compared to the actual object. Think of the number 1 as our baseline standard here. If your magnification result is less than 1, your image is shrunk. If it's exactly 1, it's the exact same size. And if it's more than 1, your image is dramatically enlarged.
Oh, and you definitely have to watch your positive and negative signs when calculating this. A negative magnification number is physical proof that your image is real and inverted. Meanwhile, a positive sign instantly tells you the image is virtual and standing perfectly erect. It's like a built-in cheat sheet right in the math.
Which leaves us with a pretty fascinating thought to take away. Given all the strict mathematical rules of reflection we just unpacked, think about your daily routine. How much of what you see in the mirrors around you every single day is a projected real image, and how much is just a beautifully structured, mathematically precise, virtual illusion? Thanks for exploring the incredible mechanics of light with me on this explainer. Keep questioning what you see and definitely keep learning.